Hi students, welcome back to the online video lectures on DSP. This would be the 9th module, and for now this would be the last module on discrete Fourier series and discrete Fourier transform. In this module we would be discussing about performing blockwise convolution, linear convolution using discrete Fourier transform. Okay, that is the objective for this module. Okay, I'll just move on to the desktop mode. A minute. Okay, so first of all, why do we want to perform blockwise convolution? Okay, why blockwise convolution, right? So there are different reasons for it. For example, see, again, the goal here is to perform the linear convolution using discrete Fourier transform. So let me for this purpose first revise a couple of things from the previous lecture. Okay, so the first one thing is, suppose I have two sequences. Let me call it as x1 of n, or x of n is fine as well. Okay, let me call it as x of n. There is one sequence of length L, whose length is L, and there is an FIR filter with which I would like to convolve it, and let that filter be h of n. Okay, and let the length of that be p. Now if I want to perform linear convolution of x of n with h of n, that would, to make it equivalent to a circular convolution, okay, circular convolution, let's say x of n circularly convolved with h of n. These two are equivalent when this n, the length should be either greater than or at least equal to L plus P minus 1. Okay, this was the condition we have worked out, and we have seen the case in the last video lecture. And we also discussed about the motivation for performing circular convolution using in the DFT domain performing multiplication. Reason being, if you could afford the conversion to DFT and inverse DFT in an efficient way, this convolution is going to be equivalent to a simple multiplication there. Okay, and you could we have worked out in the last class that if the earlier direct convolution is of order of, let's say, L square in the current context, okay, assuming that L is greater than P, here it would be order of L log to the base log L to the base 2. Okay, something of that order you could get there. So computational complexity is coming down. Okay, and make a note here, to be able to perform a linear convolution. In that way, we are saying that any discrete, so any given an LTI system, right? If you have an LTI system whose impulse response is h of n with its input x of n, so you could perform, you could get the output, the resulting output of any LTI system using DFT. So that's what it is equivalent to, because y of n is nothing but the linear convolution of x of n with h of n. Okay, that's one point we discussed, right? Suppose then the second point that we have, another important point we have discussed there is, suppose if instead of performing L plus P minus 1 point or more than that points DFT, if my n is equal to simply L, what is the consequence of it? The consequences, there are P minus 1 values. Okay, if we consider this P minus 1 initial values of the resulting of x of n point convolution with x of n gets corrupted, while of course that would give you the right result for circular convolution, but gets corrupted while you are performing linear convolution using circular convolution. So while performing linear convolution using endpoint DFT, So these are two important results that serve as basis for us. Now this should already tell you, suppose let's consider various scenarios. For example, one scenario is if you have an indefinite length sequence, so x of n, indefinite length of x of n, okay, or x of n with indefinite length. Consider this case. Assume that as my voice is getting recorded, you want to do some noise correction after that, let's say some smoothing you want to do, and of course I would be speaking, it would end at some point, but you have to, if you want to do even a simple averaging for that, unless you know the whole length L, you won't be able to make that sequence length to be L plus p minus 1, right? So indefinite length sequences would there is a problem, that's a challenge, you cannot directly use that, that's one thing, okay? And for example, another issue is that challenge could be while you are doing in the conventional DFT based approach for the entire sequence is length of x of n could be very large. What do I mean here? Assume that you are some 40 kilohertz rate, you are capturing the audio of it. Assume that this is for 1 hour duration. Just to compute even at the initial n equal to 0, you have to process then n plus L minus 1 point DFT you have to do, even if you require it at some point, right? So the length of x of n could be very large, and the n plus L minus the L plus p minus 1 point DFT that's required to compute value at each instance is going to be very large. That's another problem, okay? And another very important point to be noted here is processing has to wait until the entire sequence is acquired, until the entire sequence is captured, is it not? Because only when only after capturing the entire sequence you will know the L value. So suppose consider a case where you want to stream whatever I am talking here, okay? It's okay to stream it, let's say with a delay of 1 second, but in the conventional way of computing DFT, computing the linear convolution, so for you want to do a smoothing, let's say a simple moving average filter, to do that you want to move to DFT. For getting the correct accurate results in DFT, you have to make the sequence length L to L plus p minus 1, where p is the length of your kernel with which you want to convolve. So you have to wait till the entire sequence is captured. If I am talking for an hour, you have to wait till 1 hour to get even the result in the very beginning. So that's another challenge that is there, okay? And to deal with these things, one of the things that is done is you in fact decompose your signal into blocks and you do blockwise operation, okay? To give you some sense on why it could work, let's consider some sequence. You consider any sequence here, some sequence, okay? This is, assume that you are indefinite length, it's not infinite length, just that you do not know the length at that given point. So let's call it as x of n, and assume that you want to do simple averaging, okay? With the some filter like this, you have it, okay? I should have taken both before, after. Yeah, this is equivalent to the current instance, convolving it with would be the last two and the current. Assume I could have then 1/3 multiplication would give me a simple smoothing there. Notice here, if I have to compute value at any given point, it just depends on the value at that point, okay? So how do you convolve it? In the time domain, for example, you flip this h of n, it depends on this value. This, suppose if I am interested in computing the resulting value here, then it depends on this, this and this, just those 3 points it would depend. So there is no need to wait till the entire thing has been captured, because the value at a given point, essentially, it's, if you know its neighbors, that's good enough. Okay, that's the basic idea behind doing this blockwise operation. Okay, so this should, let me here so let's, for a moment, let's not worry about okay, let me just erase this off. Okay, just I want some space here. Okay, so what the idea is that, suppose I make it into a length of, let's say 1 2 3 4 5. This is one length here, signal of 1 2 3 4 5, and then 1 2 3, let me draw something, 1 2 3 4 5, this length. Okay, and then you keep doing like this. Okay, so this is your x of n, and so you are going to divide it into blocks, and you would like to do a blockwise operation here. So my first block, say for example, how I am going to write my blocks is, let me call this as, for example, x0 of n, this as x1 of n, and so on. So the subscript, let me call it with r. So how am I going to define here in terms of x? That's essentially will be equal to n plus r times l, where l is the length of the block. Notice here, for example, for the first block, r equal to 0, so xr of n is exactly equivalent to x of n. For the next block, r is 1, so you are going to add l here. For the next block, you are going to add 2l, and then take from there the n value. So this is true. So each is having a length of l, so this is true for n less than or equal to l minus 1, each individual block. Okay, otherwise 0. So that's how I am defining these blocks. And let your h of n be having, let the length of h of n, let me write it that way, let the length of h of n be, so p. Okay, now how do I get, so see, I'll deal with this in this way. Whatever we are going to discuss now, the first approach, which is also referred to as overlap add, is equally applicable even if you are doing linear convolution right away in the time domain. So what I would do first here is, I would explain the entire method in the time domain, followed by doing that using DFT. Okay, so let's come back to that now. Now, how do I write pi of n? Pi of n is equal to x of n convolved with h of n, and now I could write it that as my x of n is now, can you write x of n in terms of xr of n? Well, I'm just making an assumption that it's starting at 0. Otherwise also I just need to change this r value, that would be sufficient. Okay, r equal to 0 to infinity, and xr of, suppose if I give you these individual modules, how do you construct back x of n from this x subscript r of n? Well, each one, depending on if it is x1 of n, you shift it by l and add it, and then x2 of n, you shift it by 2l. Okay, you have to shift to the right, so that means shifting to the right means minus here, and depending on the r, you have to shift it, so r times l, multiple integer of this. So this convolved with h of n. Okay, now let me again get each individual output by convolving xr of n with h of n. So that, let me call this as yr of n. What I mean by that is the result of convolving xr of n with h of n. So using that notation, how can you write y of n? Y of n is equal to r is varying from 0 to infinity, yr of n minus r n. That's all. Very important result. Pay attention here. What is this result saying? You get, for example, you divided it into modules. You convolve each module with x of n, and then the result of that, each result depending on the value of r is shifted by that integer multiple of that r, r with the integer multiple of l. Okay, that l getting multiplied by with the corresponding value of r. Okay, so here you need to pay attention that suppose if I am xr of n is of length xr length of x subscript r of n equal to l, and then h of n equal to p. So then what would be the length of y subscript r of n? That will be equal to l plus p. That's the maximum length. Okay, we worked it out in the previous class. L plus p minus 1. So this summation you would have overlap. So each of, for example, you are shifting only by a value of l, but this could have a value or length of l plus p minus 1. That implies there is a overlap of p minus 1 values there. Okay, so that's all. This is what you do in linear convolution. Now let's say I would like to use, while using DFT, how would you do that? So all you need to do is now this xr of n, you have to do xr of n linear convolution of that with h of n. Okay, with which value of n you have to do? N should be equal to l plus p minus 1. Okay, what does that mean? Then only with n, then it is equivalent to xr of n linearly convolved with h of n. Of course, you will not do direct circular convolution here. Then you would of course do multiplication and come back, but then those results would be equal. So that means what I should do for that, use 0 pad xr of n and h of n such that lengths of them is equivalent to n. That's all. Okay, so this would be even becomes very much easier when you try to look at the same things with the help of an example. So let me take an example here. Let my x of n be equal to 0, 1, 2, 3, 4, 5, 6, 7, 8. I guess that's enough. Okay, so this in other words, what is the L value here? Their L value is 9. There are 9 values here. Okay, and let me take h of n here. Okay, so let's take h of n to be 1, 1, 1. Okay, let the index be starting with 0 here and with 0 here. So essentially x of 0 is 0, x of 1 is 1, x of 2 is 2, and so on. Basically n value is equal to x of n. Okay, now first step let's do is compute. So this, since you to have the ground truth or to have the basis to compare with, let's first to compute x of n convolution with h of n through direct linear convolution. Let's do that. How do you do that? You take h of minus n, right? And h of minus n would be equal to, so 1 becomes minus 1, 2 will go to minus 2, right? 0, 1, 2. Sorry, there is nothing to do with this signs. Okay, this would still remain, but this becomes your this is 0, this is minus 1, and this is minus 2. That's your thing. Okay, now so y of n, which is equal to summation of x of k into h of n minus k, k varying from minus infinity to plus infinity. Okay, anyway it will have length of 0 to L minus p plus 1. Okay, so I in fact I will change them to here, k could vary from 0. Okay, so anyway, because this value is k equal to 0 to what else, what could I take there? Okay, and of course yeah, let me keep it this way. Let's not worry about the notation there. Let me just keep whatever I have written. Okay, so what you do to compute its value at n equal to 0, you keep this 0, you keep it at 0, right? Y of n is equal to so 0 means h of minus 0 simply, so you keep it there. So there is only 0 result there. Okay, then to compute at 1 value, so you keep this center of this 1 at index 1, so you are getting 1 plus 0, so you get 1 there. To compute the value at n equal to 2, you keep this index at 2, so 2 plus 1 3. To compute at 3, you keep it there, so it is essentially sums up the previous 3 values. That's all it does. This is a kind of moving average with 3 previous values. Of course, just the 1 by 3 factor is missing, so you do that out. 6, 3, 9, 12, 15, 18, and the last one would be 21. So when you come here, the last 3 will be 6 plus 7 plus 8, 21. Okay, this, not just that, suppose if you want to do it n equal to 9, right, then 7 plus 8 you get, so that's what you get as 15. Okay, next location it would be just simply having 8 here, and of course the length of it would be equal to obviously this is L plus p minus 1, that's equal to 9 plus 3 minus 1, that's equal to 9 minus 1, 8 plus 11, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, so that's what you get. This is the value you should be getting irrespective of whatever method you are going to apply. So now let's compute that. Now compute this y of n, okay, through overlap. So this method is whatever we have discussed here is called as, this is nothing but overlap add method. Okay, so the second thing, let's compute y of n. Let's compute y of n through overlap add and direct linear convolution. And of course, then if you want to make it into blocks, you should know the length of each block. Okay, let's call with that length equal to 3. We will take the length with the L equal to 3. Let's do that. Okay, so that's what we will do now. What does that mean? So first you compute the length is L, so the n should be equal to L plus p minus 1. So this is 3 plus p is 3, right? 1 1 1 is there, minus 1, so that's 5. That means we have to do a 5-point DFT for each sequence, and this the whole sequence you call what is your x0 of. Now what do I have here? X0 of n is first three values 0, 1, 2, and what about x1 of n will be equal to 3, 4, 5. x2 of n is equal to 6, 7, 8, right? And anyway I have to do an n-point DFT, so 5-point DFT I have to accordingly zero pad that. So let me do that also. So here, so to get 5 here I would add 0 and 0, 0 and 0, 0 and 0, so that I have the values of 5 there. Okay, this is my x0, x1, x2. Okay, now h of n, let's write that. Okay, h of n is 5-point DFT, right? So you have 1, 1, 1, so I need to keep there also 2 zeros. I would zero pad it with 0, 0. So this is my h of n. Now h of minus n here, right? What would be that? Okay, here h of minus n, if you are doing it, that would be equal to, in the DFT space, h of minus n is equivalent to, what could I write here? Anyway I have to have only 5 periodic sequences I am doing that, so this would be equal to capital minus n modulo capital N, right? With that I need to do the circular convolution. Okay, I should not be calling it as h of minus n, but I should call this as h of minus n modulo n. Okay, k minus n modulo n is what I would be getting there. Okay, so let me first write for h of minus, let me call it as minus k modulo 5. Okay, n is 5, that would be equivalent to, what's that value is equal to? That's 1 would remain same. Okay, because h of 0 minus 0 would same, so then this would h of this would go to minus 1 here, right? Minus 1 means 4 minus 1, so this would 5 minus 1 4, this would go to the next value, right? And I would go to 0. So if you don't remember this, please go back to the previous lecture. So this would in fact go to minus 1. This corresponds to minus 1 modulo 5 is 4, so it's coming here. This is minus 2. Okay, 2, so that would come here, 1 0 1 1. So similarly, let me also write 1 minus k modulo 5. One more shift here, this would come to the front, so that is 1 1 1, right? And then 1 1 1 0 0 1. What about h of 2 minus k modulo 5? One more shift, 1 1 1, this comes to the front, so last 2 zeros. Let me finish this off. H of 3 minus k modulo 5, one more shift, so 0 would come here, 1 1 1 0. Last one, 4 minus k modulo 5, the 0 would come to the front, 0 0, and there are last 3 ones, right? Okay, now I would like to compute here y1 of n. y1 of n. How do I get that? Right. So first I need to x0 of n. I need to do with compute with so without any h of minus k with that. So that should take sum of the last two and the first one. Okay, multiply and take the sum there. So that would be equivalent to last two and first one, they are all zeros, so I would get here 0. The next one, y1 of 1, so that means shift by 1, so first two and last one I have to take in this, first two and last one, multiply and add, that would be equal to 1. Okay, so then 0 1 2, okay, first 3 you have to take, anyway multiplication with 1 and add is equivalent to directly adding, so add first 3 values of x0 of n, that would give you 3. And then next 0, what is the next one? You 1 0 1 2 we are done, 3, so second third fourth you add there, so that's 1 2 0, that's again 3. Okay, the next one is 2 you get, so add last 3, that would give you, adding last 3 would give you 2. Okay, so then y2 of n, well I am just try to see y2 of n, while adding there I need to shift it by a factor of L there, if you recollect. See, I need to shift it by L being here 3. So once I do it, it should start, it should get, I should shift it by 3 to the right, so it would start adding from here. So x2 you multiply with this one, so last 2 and first for x2, x1, so last 2 is 0, so this is 3, and then n equal to 1, so 1 means first 2 and last one, first 2 is 4 plus 3 7, and the last is 0, so this is 7 0 1 2. 2 is first 3 values, x1 first 3, 4 plus 3 7 plus 5 12. You continue that, you would get, you work it out yourself, I am just putting the values directly, 12 9 5. Okay, similarly y3 of n, you do it, this would again shift by 2l, correct? So 2l is so essentially here last 2 values here it would come here, and this would be equal to 6 13 21 15 and 8. Okay, and what is it that you, how do you get y of n? So by the way, this anyway, this is the origin for it, this is the origin for it, this is the n equal to 0 for it. But now what you do, summation of for r varying from 0 to infinity, y of n minus r times l, your l being equal to 3. Okay, then that do it, you shift by l, you shift by 2l, so I already placed them like that, so you just keep adding it, 0 1 3 6 9 12 15 18 21 15 and 8, same as the previous one. That's how you get it. Okay, hope this is clear. Okay, this method is called as overlap save method. So just let me before I move to the other method, sorry, overlap add method, so let me just show you a slide also illustrating that, should help you in case if you the same. So there's a summary for this. Okay, quickly go through that. Okay, x of n plus rl, we have written that. Okay, this is how we have written this, you are done with it already. So this is x naught of n, you have taken into a length of l each one, and you zero padded it with p minus 1 values, right? And then you were that is how you have written x. So from x0 whatever output you got is, for example, y0, that again shifted by l value you do for x1. Again notice here this starts from 0, except that for convenience we have drawn it that way. Okay, and then you got them, you sum them all, and that's it. Okay, hope this is clear. Let me come back to now the next method, which is called as another very important method, overlap save method. Okay, whatever we have seen now is overlap add method. Now we will see overlap save method. The idea of this method is like this. This is essentially based on what we mentioned here. If you consider n equal to L, so the just whatever length of the block you have taken, p minus 1 values are corrupted. So that too initial values are corrupted. The idea is very simple. Since initial values are corrupted, you take only an L point DFT, but make sure that the sequences you are considering have overlaps, and that overlap exactly equivalent to p minus 1. That's all. As simple as that. Okay, so let me show you the same thing here. Again, we assume that L is greater than P, otherwise more values would be corrupted. So look at here. You have taken a sequence of length L, but the next sequence, so P minus 1 initial values would get corrupted. So you take such that there is an overlap of P minus 1 values here. So you could see here L minus of P minus 1, and from there this is there. And anyway, those values, initial P minus 1 values for these n values would be corrupted, but nevertheless they will be correct in the other one. So for example, this is x0 of n. Okay, this gets corrupted only this side, not on the right hand side. So you just retain the values from the earlier sequence, and the next sequence the initial values you ignore. And you might ask the question, how about this beginning, right? You simply take from, instead of taking it 0, here you take another L minus 1 values, so minus 1, minus 2, up to the length being L minus 1, and you are done with it. That's all. This is very simple. So what you are going to do, for this you compute it, the initial L minus 1 you ignore, and make sure between each block there is an overlap of P minus 1. Okay, and when you compute that, the next time you ignore these P minus 1 values. Okay, and there is no summing as such. Then you concatenate everything, and that should give you the result. Okay, so assumption is L greater than P. Each block is of length L. P minus 1 samples are overlaid between the adjacent blocks, and then perform L point circular convolution, and after that you save L minus P plus 1 values. Okay, in fact there is no need to compute the circular convolution for the initial P minus 1 points, because you will anyway drop those values. Okay, as simple as that. So I don't want even writing equations and all is not necessary here. So let me right away go to solving problems, because that should make things very clear. Okay, so let's take the same example as previous example, but now in this example all I would do is, let me take perform linear convolution. Okay, so perform linear convolution for the previous example itself, using, now let's do it using overlaps previous example, using overlap save, and with L equal to 5. Okay, make a notice here, the L value. So let me quickly write here, your x of n is equal to 0, 1, 2, 3, 4, 5, 6, 7, 8. Okay, and your now it's an L point DFT. So your n is equal to L. That means you are going to perform a 5-point GFT. The initial L minus 1 values would be dropped. So what I would do here for x naught of n is that L minus, or L plus P minus, so P minus 1 equal to how much? 2, correct? So how do I consider x0 of n? I would append here 0, okay, and 2, and then because these anyway, otherwise at n equal to 0 and n equal to 1 I would get wrong results, so I am simply appending by 2 there, okay, but my origin could remain same. This is my x0 of n. Notice here it has sequences of length this, x1 of n, there should be an overlap of 2, correct? So this should start at 1, 2, so that this overlap is there, 3, 4, 5, okay, and of course then this is the origin here. What about x2 of n is equal to, again 2 overlap should be there, so let me take this as 4, 5, 6, 7, 8. Hope that is clear. Now I could in fact write h of n here itself, so that h of n equal to 1, 1, 1. I would like to endpoint DFT, so I would append 0, 0, right? Anyways, the first two values are corrupted, so I don't have to do h of minus n and h of 1 minus n, so I could directly do from h of 2 minus n, okay. How do I compute that? So anyway, for the easy to follow it easily, although I won't use h of minus n, writing that would make my life easier. So minus n means this one would remain same, this would go here, the second one would go here, then 0 would come, 0 would come here. So then the rest of the story would become easier. So let me, since I won't be performing minus n and 1 minus n, I'm writing 2 minus n here, which would be equal to 2 minus n means you shift 2 values here, okay. So that means 1, 1, 1, and followed by 0, 0. It is 2 minus n. H of 3 minus n, you shift one more value here, brings 0 here, 1, 1, 1, 0, okay. H of 4 minus n, you make one more shift there, you bring that 0 as well here, 0, 0, 1, 1, 1, okay. Now let's compute x0 of n, okay. As I mentioned, the first two values are anyway corrupted, so I am not interested in even calculating them, okay. The next one is at this point, okay. So n equal to, you could consider as if this is your starting point, okay, that's fine. So that would be equal to, I should multiply it with shift, so this is 0 minus n, 1 minus n, 2 minus n. So you multiply with 2 minus n, you sum up the first three values, that's giving you 0, right? So this I would y0 of n, I would get 0 here. So next one you multiply with the 3 minus n, so you take last from the last, second, third, fourth, okay, these values, that would give me 1, okay, and then 4 minus n, you sum up last three values, that would give me 3. What about x1 of n? Again, you don't calculate the first two values, okay. Let me, otherwise would write it here itself. So you don't compute the first two values, okay. Anyway, later you would be shifting by L. So I'm just writing it, you would be making that shift, okay, first with the overlap is there, of course. So this 2 you won't get it, you ignore that. The next one, you multiply it with 2 minus n, first 3, 1 plus 2 plus 3, that's equal to 6, and you would get here 9. Similarly you do it, you get it here 12. And what about x2 of n? You ignore the last two here, okay, and then you would be getting here, you'll be getting there x2 15, 18 and 21. Okay, 15, 18, 21. Okay, of course there will be two more values there. Okay, so in fact you have to do one more overlap you have to consider here. Let me check that out. 6, 7, 8, 1, 3, 6, 9, 12, 15, 18, 21. What was the issue here? Yeah. So will there be any x3 of n is required here? Let me cross check that here with this diagram. Okay, so yeah, no, that's fine. So anyway the last two gets corrupted, so with this you would still miss. I need to append perhaps zeros. Just pay attention there to that part. Okay, so what do I get here now? That implies your y of n is equal to, you start from, anyway this is your origin here, so that's, you added zeros there, so 0, 1, 3, 6, 9, 12, 15, 18, 21. I guess you need to please pay attention on what exactly needs to be done. You would be getting these two are missing at this point, so that I guess you have to take, just write out, let's try it out, x3 of n, you would consider it as again two values, so 7, 8, okay, 0, 0, 0, because the length could be more. With that, if you compute here, one minute, yeah, so okay, yeah, so just if I do x3 of n also here, because I had to get the last results there, so otherwise 5-point DFT would give you the 5 points only. So what should I do now? This will anyways, last two gets ignored here, correct, and then the next one would be multiplication with 2 minus n, correct. 2 minus n is first three values, that would be equal to 15, 18, 21, and then yeah, last two values. So this 2 minus n, three values, that will give you 15 here, that's 15. Okay, and then the next one is the middle three values, right? So middle three values is 8 here. The next one, last three values, that's 0. Okay, that's all. So you now add everything. Okay, so 18, 21, 15, 8, and of course after that this is going to be 0. This is your y of n. You can cross check it with the earlier ones. See, by the way, what I missed in the very beginning is that I didn't realize that this length could be more than, it could be up to n plus l minus 1. So I should have been append, because 5-point DFT would give you just 5 results. I should be in fact appending it with 0, 0, okay, l plus p minus 1, which is 2. That's all. With that you have done it, and this is all we are done. So let me come back. Okay, okay, so with that we are done with the DFT part. So we will this has been so let's see. Hope this is clear to you. If you have any questions, you please post them in the comment section, or you get them clarified in the Zoom session. Okay, yeah, thanks for watching. Take care. Bye.